In this video, we'll be demonstrating how to implement simple linear regression in matrix form in R. So first of all, you can go and review our document for Introduction to R at the beginning of the Blackboard course to get a feel for what the matrix multiplication in R looks like. We're going to do a bit of that here, but if you want a bit more support, feel free to use that. So first I'm going to make a matrix. It's just kind of a nonsensical matrix of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, split into 3 columns. Now the star operator in R is element-wise matrix multiplication. So if I did x times x, what that would give me is the first element of x times the first element of x, the second element of x times the second element of x, and so on, which is the way in which we approach addition in matrix form, but not the way in which we do multiplication in matrix form traditionally. So to do multiplication in matrix form traditionally, we use the, the percent sign, then the star, then the percent sign. And this tells me that I want to do multiplication in matrix form, not multiplication in scalar form. So in doing this, I see that I get a very different result doing x percent times percent sign x than x times x. So this would be 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, or we're just multiplying those by itself. In this case, recall that we're taking the rows and then the columns and multiplying those together, then adding them all up in the way in which we demonstrated in the notes. Okay. So also recall that, let's say we make a different matrix Z, which is a 3 by 2 matrix, that sometimes our dimensions cannot line up and that there are matrices that we can't multiply. I mentioned in the video lecture set as we were talking through those slides that sometimes in R you get the error of non-conformable arguments, and this is a great example where that actually happens. We get this error non-conformable arguments. This does not mean that you broke mathematics. This means that you're trying to break mathematics by multiplying matrices that can't be multiplied, and the reason that this can't be multiplied is because the number of columns and the number of rows are not the same for the first and the second column. And again, you should revisit the lecture notes to see the details about what we mean by conformable arguments and how we go about making sure that our matrices can be multiplied. The transpose function in R is just T. So we wrap our matrix Z in T and we get that matrix transpose. Again, like peeling a piece of paper from the bottom left to the top right, where our columns become rows and our rows become columns. Now, if we take matrix transpose times the matrix, those are always conformable arguments, and we can do that. Again, we do x transpose x in our solution for the parameter estimates in regression. Now, to find the inverse of a matrix, so I'm just going to calculate 9 random normal numbers. Yours are going to be different. That's okay. Actually, I suppose we can do set seed here to make sure that all of ours are the same. Set seed 1. So now, if you run this, ours should be the same. This negative 0.62. To find the inverse of this matrix, we use the solve command. So in this case, solve, this finds the inverse of the matrix A. Now, the method by which it does this, we're not really going to discuss in class. I don't think we even discussed the inverse of simple matrices in our slides. It's not particularly important. However, the definition of what an inverse means is rather important because it was used in one of our matrix proofs. So recall that when we multiply any matrix times its inverse, that gives us the identity matrix. So when we multiply A times the inverse of A, that gives us the identity matrix. Now for a square matrix, so for X, because the columns are not linearly independent, that is column 2 is just column 1 plus 3, and column 3 is column 1 plus column 2, or excuse me, column 2 is column 3 minus column 1, and column 3 is column 1 plus column 2. This isn't going to find a solution to the inverse of the matrix because we don't have that full rank matrix. Also, when we try to solve a matrix that isn't square, such as the matrix Z, which is not a square matrix, then we run into issues. So R can't break math to find the inverse of a matrix for you, so remember your matrix inverse rules from the notes that we talked about. Last but not least, we talked about the covariance matrix a fair amount. So the covariance matrix in X, we looked at the relationship between all the different components. In R, we calculate the covariance matrix for a vector or a matrix via using the cov command. So COV finds the covariance of our matrix. In the same way, actually, we could use the COR, which finds the correlation of our matrix. Again, the correlation is kind of like a standardized version of the covariance. Covariance is more unit tied than the correlation is. But we tend to use covariances in our calculations because we use variances in our calculations. So this is just a quick reminder. Some, even most of this, I know is in our Intro to R document that we presented at the very beginning of class. But I do want to remind you of how to do matrix multiplication, how to find the inverse of a matrix, and how to find the covariance of a vector before we get going with our example for today. So for our example, I'm going to hit Control L and clear out the screen here. The example is air quality in cars. So what I'm going to look at is I'm going to look at the, or excuse me, not air quality. We're going to just look at the cars data set and look at the distance that it takes cars to stop and the speed at which cars are moving. So the distance that it takes cars to stop ideally can be predicted by the speed that cars are moving. So distance is going to be my outcome or my y vector. In this particular case, when I'm making my x, recall that x in matrix form is no longer a vector. X in matrix form is a matrix. It is called the design matrix, where we have a column of ones and then a column of our x values. And if I had multiple x values, I would list them here. So let's say I had a different x value, x2, that would go here, and then x3 and x4 and so on. We don't have this in this example. We're not talking about multiple regression quite yet, but that's where that would go. So when I look at y is my vector of y values, and x is my design matrix. It's a matrix, and it's always a matrix. X is never going to be a vector anymore in our matrix form. So for our calculations, we had a few things that we had. We had x transpose x, then we had x transpose x inverse, xt xi is how I'm denoting that. And again, x transpose x times x transpose x inverse should give me, to within the rounding error, the design matrix, and it does to within rounding error. I have x transpose y, and then to find my b value, I have x transpose x inverse, so xtxi, times x transpose y, which I already have written. So this is my predicted beta. Now I'm going to look at this and compare this with what I would get using the lm command. Note that because x is a matrix, no longer a vector, I can't just do y squiggle x anymore. I have to give it the vector from the x matrix of my independent variable. So it's the second column. So I'm just asking for the second column of the design matrix in the lm command. The hat matrix is something that we calculated previously, and I can find y hat and compare that to hat times the y's. Now this was the first way that we talked about y hat, and x times b. So if I look at these side by side, I guess I should name these differently. I'll call it y hat sub h and then y hat sub b, indicating the two different ways in which we're calculating these. So y hat sub h and then y hat sub b, we can put these side by side and see if they're the same. And what we see is that both of the predictions on the different y hats are exactly the same, whether you use the hat matrix or the predicted betas. Now residuals are just y minus y hat, and again there were several different ways in which we could calculate these, but we'll just keep it simple. The y vector minus the y hat vector. The mean squared error, I'm going to start by calculating the length of y. Now note that I can't just use the length of x. So if I look at the length of y and then the length of x, I'm going to get two different results. And the reason is because, recall what y looks like. Y is a vector, but x is now a matrix. X isn't a vector anymore. So if I wanted to use x, I would have to use in row of x, that is the number of observations in x, because otherwise it's going to double count. It's going to count 1 and 4 as two different observations. So if I have two different observations for each of the 50 participants that I have, each of them count twice, I'd double count them, and I'd end up with falsely claiming the sample size is 100. To prevent that, I'm just going to look at the length of the y vector, because I know that's always going to stay a vector. For the sums of squares of error, I'm just going to do the transpose of the error times the error term, and then the mean squares error is the sum of squares error divided by n minus 2. So I can calculate the MSE. Note how much quicker this is than previous calculations of the MSE. All I do is I take my residuals, transpose of the residual times the residual vector divided by n minus 2, and just like that I have my MSE calculation. Really, really straightforward. Comparing that to what I get in the model, I see that these absolutely line up with what I get from my linear regression model. Now let's dive into the covariance matrix for the parameter estimates. So the covariance matrix for the parameter estimates is the MSE times x transpose x inverse from our notes, the square root of the covariance matrix. This is the standard errors. Now note that not everything, I can't take the square root necessarily of the off-diagonal elements. In this case they're negative. They're not always going to be negative, and this isn't always going to be nan. But I don't really care about the off-diagonal elements because it's the diagonal elements that tell me what my different components are. So let's walk through this because this is important to realize. Again, first of all, the covariance matrix that we talked about in class in the lectures is important because the square root of that covariance matrix tells me the standard errors of my betas. Now we can have a covariance matrix of anything. We can have a covariance matrix of raw data, etc. But the covariance matrix for my parameter estimates, the square root of that covariance matrix gives me the standard errors. Now what are the standard errors? In this particular case, the standard errors are the diagonals, where the first diagonal or the first diagonal element is the standard error for the first parameter. In our case, that's B0. The second diagonal element is the standard error for the second parameter. In our case, that's B1. And then if I had more parameter estimates, I'd have more diagonals, and I would just keep reading off the diagonals. Sometimes it can be handy if instead of finding all that, I just type diag, which gives me the diagonal, and then I can do square root covariance matrix B, and that gives me the diagonal, so I don't have to worry about reading all of these big matrix elements. I can just look at those diagonals elements. Now, what are these? Well, again, the square root of the covariance matrix, this is the standard error of B, and if you look back at our notes from lecture 3, I believe lecture 3 is when we started talking about parameter estimates, the standard errors, statistical tests of parameters, and confidence intervals might have been lecture 2. But look back at one of our very early lectures, we discussed the importance of the standard error of the parameter estimates. So looking at the standard error of the parameter estimates, we can see that this is the way in which they're calculated in matrix form. Again, very, very, very simple in comparison with everything that we went through previously. Looking at the summary from the model, I can compare that to the standard error that's calculated by R. Recall that the t value is just the estimate divided by the standard error. And again, this is what creates our t statistic and calculates our p-values for each of these. This is why these standard errors are so important. Comparing the standard errors to what I calculated in matrix form, I see 6.758, 6.758. Those line up perfectly. 0.415, 0.415, those line up perfectly. So our matrix form calculations perfectly line up with what we see in R. Now for the sums of squares, again, this can or cannot be important. I won't say it's not important. I'll just say that for the sums of squares, they have a very specific use. This is probably one of the more important things that we have, being sure that you can calculate, let's see, where did we do it? Where we calculated our betas, our parameter estimates, that's really, really important. Down here where we calculate our standard errors of those parameter estimates, that's really important. And again, if you think about what we tend to look at in regression, I look at my parameter estimates, which is that first calculation, and again we showed that previously. I look at the standard errors of those, and then I do combine these in a way that we talked about way back in the day, again in some of our earliest chapters, to create t-statistics, calculate p-values. So these are the most important calculations in matrix form that I really, really want you to get. But the sums of squares are useful when we start talking about things like ANOVA. So for sums of squares, I'm going to have to make that J matrix. And again, J matrix is a matrix of all ones that's n by n. So this is a huge matrix that doesn't even fully display it on my screen. Maybe I can do view J. So that we can see, but it's just a huge matrix which is all ones in it. So that's all this this matrix is just a big matrix of ones. The sum of squares of total is the transpose of y times y minus 1 divided by n times the transpose of y times the J matrix times y. So this is the sums of squares total, sums of squares error, and the sums of squares residuals that I can calculate using my J matrix. Note that the sums of squares residual plus the sums of squares error should add up to be the sums of squares total, and we see that in this case that is absolutely true. Note that we can also compare this with the ANOVA function in R. If I type ANOVA and then my LM of y and then x, just the second column of x, I see that my sums of squares regression is 21,186, and then my sums of squares residuals 11,354. Comparing that with my sums of squares error 11,353. Well, and we can even see more accurately than what R provided us by default that this was 53.5, and R just rounded it up to 54. And then the sums of squares residual 21,185. Again, we can see that there was some rounding issues going on here. So in this particular case, we can see how these break down, and we can see how our matrix forms calculated give us the components that are in the ANOVA table. Now we can also use the quadratic forms. So again, we have the I identity matrix, which is the matrix of zeros with just ones in the diagonals, similar to the J matrix, except the J matrix is all ones. The identity matrix just has that diagonal of ones. And then we can calculate the quadratic forms of the sum of squares regression, sum of squares total, and the sum of squares error. We see that the quadratic form of the sums of squares regression is the same answer as our original sums of squares regression that we calculated in matrix form, and same thing with the sums of squares error and the sums of squares total, that whether we calculate them using the original forms that we presented in matrix forms or the quadratic forms, we actually get the same responses in both. Now this has been a quick run through of how we implement simple linear regression in matrix form in R. It is kind of important to understand the components in which we create these, and I'll even say that many of these forms are the ways in which some of the functions that you use in R actually implement regression. They don't implement regression using those big long calculations that we kind of did at the beginning. They implement regression by creating these matrices and then multiplying these matrices together in ways that give us a whole list of answers just using a few simple matrix calculations. So we've kind of extended it previously, but if you kind of look at how quickly this would be combined, we would just have solve transpose x times times transpose x times y, and that would be the answer for B. I mean, think about all of we had tens of lines of code calculating B previously, but that's all you would do. You could calculate this vector of B's in a single line. It is very, very, very cool. And we're not even talking about how difficult this would be to calculate if we had many, many, many parameters in our statistical model. So this is a really, really cool implementation. Again, this is how many softwares implement least squares regression in the back end of their software, is using this matrix form because it is so generalizable and so easy to use. The next video, again, we will dive into the multiple linear regression and how we can start using, implementing, and interpreting multiple linear regression now that we've covered this matrix form and the calculations needed for multiple linear regression.